reactions we have discussed so far. We'll start from there and we'll see where we go. So first one which you're talking about is LiLH4, right?
Yes, sir.
Okay, LiLH4, we have some doubts about how LiLH4 is actually going to be working. Is that correct?
Yes, sir. Yeah.
Okay. When we say actually working, what do you mean? What is the exact doubt here?
He gave us the mechanism, and then that is fine, but like
See, LiLH4 here is going to be something which is going to be actually a mixture of lithium hydride and ALH3. Okay.
Yeah.
So what happens over here is the LiH here can more easily break down into Li plus and H minus when the H minus is in the presence of something which will stabilize it. H minus is not normally stable. Okay. So H minus is not that stable. That is the reason why it doesn't break that easily. Here, though, there is something like ALH3, which is available over here, which is going to be stabilizing the H minus.
Electron diffusion.
Okay, so this mixture together is actually something which you can think of as H minus in ALH3. Now, H minus in ALH3. ALH3 here is going to be having its central figure here being the aluminium, which is going to be having a coordinate covalent bond right now with the, hydrogen in the form of H minus ion. So the ALH3 here is going to be having a coordinate covalent bond with the hydrogen, which is the part of the H minus ion here, with the H minus ion here. So what happens in this case here is the attractive force between the aluminium 3 plus ion and the H minus is what is going to be determining how strong this LiAlH4 is as a reducing agent. Because when it is behaving as a reducing agent here, so if I have to consider this as a reducing agent, the basic idea here is this fellow has to release H minus. And that H minus should go attack as a nucleophile. That is basically the game when you're going to be having this LiLH4 behaving as a reducing agent. Now, when you mentioned that you have some confusion regarding LiLH4 behaving as a reducing agent, I'm assuming that had some connection with the NaBH4 also, or is it not having any connection?
I mean, it was like specific to this this reaction.
Okay, give me the reaction now specifically.
Sir, like it was just like he gave the mechanism of how ester is reduced by ALH4.
Ester,
yes. And then before that, he also gave how, like, once the ester reduces, it reduces to this aldehyde, right? So the aldehyde, again, it reduces to alcohol. So he asked us for one molecule of ester, how many molecules of LiLH4 are needed? He said 2 are needed, but then how is it?
Think. So let's say I am having an ester. Let's take a simple methyl ester. Okay. If I want to perform a reduction of this with H minus. Okay. What happens over here is the first H minus
carbon
will come and attack this.
Yeah.
As expected. It will perform a nucleophilic addition, resulting in this guy being formed. Yes?
Yeah.
Now, this step is reversible. Yes or no? It's a nucleophilic addition step. All nucleophilic additions reactions are reversible in nature. All acid-base reactions are reversible. All nucleophilic addition reactions are reversible. Okay, so this is a reversible step. In the next step here, what is going to be happening is this O minus here has got 3 lone pairs now. Correct?
Yeah.
One of them will shift inward here, and these 2 electrons will be taken over by the oxygen here, which already has 2. And we end up having this oxygen basically leaving outside.
Okay.
Okay. So now, in this next step, what is going to be obtained as a product here? You'll be having R,
This aldehyde.
yes, C double bond O H. And we are going to be having this oxygen here, having the 2 lone pairs left over. This is this oxygen, number 1.
Yeah.
Okay. Where is oxygen number 2 now? On the other hand, oxygen number 2 has gotten out
Methanol.
in the form of CH3O minus, where it has got 3 lone pairs now for itself.
Okay. So is that O minus again attacked by the...
Stop. Let us now look at this particular reaction again now a little bit more closely before we move further. This reaction here, look at the backward direction of the reaction. What is the forward direction here? That is, if I look at it from this direction point of view, what is the reaction? Huh? Elimination. It is basically the leaving group is leaving.
Yeah.
Correct? Huh? So nucleophilic elimination is a way to look at this.
Okay.
Correct?
Yeah.
Now look at this direction now.
Nucleophilic addition. It will be.
Now think about what happened over here. Nucleophilic addition is reversible.
Yeah.
Basically, this step which we are looking at currently is also reversible then.
Yeah.
Correct? So does that answer your question before it even starts? Yes or no? Can the CH3O minus go attack again? Yes, of course. That is reversible part there.
Yeah.
Fair or not?
Yes, sir. Yeah.
Now, in this process here, we have consumed how much of this?
1 equivalent. Yeah.
Okay. Yeah?
H minus from LA.
For what we have currently. We have an R C double bond OH. You're saying something just now.
That H minus is from LiAlH4 minus.
Yes, of course. Yes, of course.
Okay.
This is absolutely from LiLH4. Now, we have got the aldehyde in stock right now. This aldehyde can now react with another H minus from LiLH4, of course. Okay. And this particular H minus will now again go and perform yet another nucleophilic addition reaction.
Same reaction. I mean, yeah. But
Not-
no leave this time.
Well, yeah, from principle it is the same,
Yeah.
but different products are going to be obtained. In which case we'll be having RC. Now we will have 2 hydrogens attached and I will have an O minus. The O minus will of course have 3 lone pairs of oxygen, 3 lone pairs of electrons on the oxygen. Because one of the pairs of electrons now ends up being taken over and becomes a lone pair here.
Yeah.
So this is basically what is going to be happening in this case here, which of course is then going to be accepting a H plus from water when you end up performing hydrolysis, either from H2O or from H3O plus, whichever way you look at it, you'll end up having this fellow basically ends up accepting and will end up becoming RCH2OH. Of course, what is going to be happening? This step is an acid-base neutralization. So what does that mean?
Reversible.
Reversible.
Sir, our teacher kind of just a second.
Now have a look here. How many moles is going to be consumed here? In this step here, 1
2
mole
only.
is consumed.
So 1 plus 1, 2, yeah.
Hmm.
But then he gave us like, I'll just send it.
Wait a second, let's finish off, then you compare. So basically, if we are going to be having ester,
1.
RC double bond O R dash. If I hit it with LiAlH4, all right, with 1 equivalent, I will end up having the product being RC double bond OH plus R dash O minus. If I hit this guy with 1 more equivalent now,
Alcohol.
then I'll be getting RCH2OH.
Okay. Yeah.
You understand the process here?
Yes, sir. Yeah.
Now ask your question based on what your teacher has done in school.
Just a second. It's not exactly the same, but I sent it, sir.
Yeah. No, no, no. This is. Are you sure your teacher gave you this?
That's what I copied, sir. Yeah. Like the signs might be wrong, the plus minus.
Yeah, that is the problem. That's why I'm asking exactly kya hua hai.
I may have copied it wrong, but I was also like,
See,
no,
see,
I'm
see.
pretty
Stop,
sure.
stop, 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 stop. That is not the point over here. Doesn't matter. Let me just quickly explain to you what is the correct, exactly what is given there. Now, in this step here, you see this step marked here?
Yeah.
So in this step over here,
Instead of OH,
yeah. Basically, what is this guy?
nucleophile.
Oh, let's call this as species 2. Let's call it as 2. Let's observe it a little bit more closely in the next page. So we're going to be having R CH2O minus, correct?
Yes, sir. Yeah.
It has now currently formed by the attack of H minus on the aldehyde, correct? When the H minus attacked the aldehyde location, we had RCH2O minus formed at that instant.
Yeah.
Right. So when that formed over here, now you have this O minus produced right now. What else is present in the medium?
The
What
AL.
simultaneously? Your
AL.
LiAlH4
Yeah. Yes.
originally broke up to become Li plus plus AlH4 minus. Correct?
Yes, sir.
Each time the AlH4 ended up reacting, it breaks into a H minus and
AL.
H3.
Oh,
So on
okay.
and so forth. Because the ion which is present is aluminium plus 3. Okay? Aluminium plus 3 is the ion which is present. It can form a particular coordinate covalent bond with either the H minus present here or with the O minus.
O minus.
Either of the two. It doesn't give a shit in the beginning. In fact, it prefers the O minus more than the H minus. Why? Because aluminium is more metallic in nature, meaning it prefers something which can hold the negative charge in a better manner.
More electronegative that. Yeah.
Exactly. So oxygen is basically a much more preferred partner for the aluminium 3 plus ion. So what is going to be happening here is you're going to be having the aluminium 3 plus originally was something which was present in the form of AlH4 minus 1. It is trading the H minus ion, which is not good of a partner, for a better partner. What is going to be the final state in this particular case here? It is going to be present as Al O CH2 R entire thing minus 1. There are 4 of these.
Okay.
But where is the negative charge? The negative charge is on the goddamn oxygen. All right. The negative charge is on the oxygen here, not anywhere else. There are 4 of these here. The negative charge is going to be on the oxygen here individually. The aluminium is going to be with a goddamn plus 3. This is a coordination complex. Okay. Now this fellow is the one which we are undergoing hydrolysis with.
Okay.
You understand the idea here?
Yes.
When
Sir.
we do that, we will end up having RCH2OH uptake.
4 moles.
For every 1 full mole of this compound, you get 4 moles of this guy.
Yeah. Then in that case, won't we need 1/4 moles of LH4?
Equivalents, not moles. Moles is different. You're confusing equivalents and moles. Look at the terminology I've used here. Very carefully, I put one equivalent in every spot. One equivalent now, one amount of H minus. So N factor for LiLH4 is 4. So yes.
4. Yeah.
So LiLH4 N factor is 4.
Yes.
So if I'm going to be having, say, ester plus LiLH4. Technically speaking, when you're writing the equation, you have to put it as one equivalent. All right. So 2 equivalents now, we will end up having product obtained as RCH2OH plus R dash OH.
Okay.
And how many moles we'll be having balancing wise? 1 mole of ester requires 2 equivalents of H minus. So 1 mole of ester needs 2 equivalents of H minus. 1 mole of LiAlH4 provides how many equivalents of H minus? Can provide 4 equivalents of H minus.
Yeah.
Okay. So what will happen now? That means you'll end up having balancing wise 2, 2, 2. You understand the idea here?
Yes, sir. Yeah.
Really?
Yes, sir.
Why do I not see shit on your face properly getting convincing?
I got it, sir. I got it.
Okay, what else next? Now, with what acid derivatives will this reaction happen?
What's that? I get it.
Ester ke saath you talked about a reaction now, correct?
Yeah.
So now my next question is, with which other acid derivatives can this happen? When you consider acid derivatives.
Oh, acid halide. Like that?
Good, yes. Acid derivatives are going to be your derivatives formed from acid. So ester.
Carboxylic acid.
Will that give?
Yes.
Carboxylic acid with what?
With LiLH4.
What did you learn about that?
I don't think it gives reaction actually. Right?
Yes, it doesn't react.
Yeah, it doesn't. It's very less reactive. My bad. Yeah.
What is the reaction between these two?
It won't react. I mean, very less yield.
Stupid bugger.
Sorry, it will react, sir. It'll give alcohol.
No. It will react, yes, that is true. But not to give alcohol. What will be the reaction?
Acid-based reaction.
Nothing else will happen. No redox. Okay.
Okay.
Now, if we are going to be having the ester with LiLH4, in this case here, 1 mole reacts with 2 equivalents to give product as alcohol.
Yeah.
What other acid derivatives do similar reactions? Ester ke liye it works, yes. You mentioned one more. Acid
Acid
halide.
halide.
That is also true. So acid
Uh-huh.
halide, let's see what will happen here.
Hmm.
Acid halide, what will happen? Let's take the acid halide.
1 mole is enough, I guess.
So in this case here, how many equivalents?
No. 2 equivalents. Here also.
2 equivalents here also.
Cl will leave.
So 1 mole is going to be requiring 2 equivalents here as well.
Hmm.
To finally give you
Alcohol.
RCH2OH.
Hmm.
Right?
Yeah.
This is going to be the product obtained over here. So in this case also, it is going to be first acid halide. Then you get what? Aldehyde. Then you get alcohol.
Alcohol, yes.
Fair?
Yes.
Now, how about some other acid derivative? How about an anhydride?
Anhydride.
Let's say I have an acid anhydride.
Yes, I think this will do. 2 equivalents.
Think and then answer. Use your brain first.
Sir, what's the exact question?
Can this be reduced by
LiLH4.
NiLH4 properly, completely? And if so, how many?
1 second. So to get like 2 different alcohols that form, right? I mean, if let's say it does react, then 2 will form. So like, are you asking?
You think and tell what are possibilities. Do not try to give me an answer. Try to give me possibilities. Create the options.
Okay, then first like it's an SN2 reaction, so it'll attack wherever the R is
SN2
small. Yeah.
What is the mechanism we have been seeing till now? It is called nucleophilic addition followed by elimination. Look, I'll show you. In this year, when Esther was doing here, what is this two-step mechanism called? Look at the process. This is a nucleophilic addition. This is nucleophilic elimination.
Additional elimination.
Okay, so this particular reaction here is actually called as nucleophilic addition elimination.
Oh, sorry, this is not SN2. My bad. No. Something else was SN2.
So this entire two-step process, this is the addition elimination reaction.
Okay.
All right, so all acid derivatives do this mechanism. Now,
Okay.
what
Yeah.
will be happening here?
Then in this case, it could either the H minus will either attack either of the carbons. So and then once it attacks this O, that ester group will leave. Like, and then you'll get an aldehyde, and then
That is mechanism.
yeah.
My question is, what is the final analysis?
Okay, then 1 second.
Okay, good. You're doing the right thing, putting pen to paper. It's nice to see that you're doing that. Yeah, but let me just quickly give you the analysis here anyway. The analysis is going to be, yes, you will have two possibilities. In one case, you'll have 2 equivalents consumed, and you can get one of the 2 products, RCH2OH.
Or R dash.
Yes, or R dash CH2OH. Plus, you'll be getting, of course, the other fellow. In the first case, R dash CO minus you'll be getting. In this case, RCO minus you'll be getting. Or if we are somehow able to, how to put it, to extract from this also, because these two are also possibilities from which we might be able to extract the LiLH4, or from which we might be able to get the corresponding alcohols as well. So if I'm trying to get it from this also together, then if somehow or the other, if they are giving, say, some 4 equivalents type of shit, what will happen in that case? Yes,
Each of them would require.
probably make up that you'll have both sides basically undergoing reduction completely.
Yeah.
How it will happen, it's not particularly clear. Why is there a problem with how it happens? Mainly
Too
because
many.
RCO minus, when you perform hydrolysis, it will end up becoming RCOH or R dash COH,
Which is slowly, which will not be reactive.
only does acid-base reaction with LiLH4, which is basically the backward.
Sir, how did you say that LiLH4 will reduce this thing? Like, is there a solid way to tell?
Which one?
This you asked first of all whether it will reduce acid anhydride, and then you said if so, then
Can you explain which part you had a confusion on? My
no, sir,
usage of words?
you said you asked me whether first of all will LiLH4 react with reduce acid anhydride, and if so, how many equivalents? So how do we know exactly that it will do it? It will reduce.
We know for a fact this is going to be something where there are, what to say, locations which are having high delta plus.
Yeah, but even for RCOH also there is a place like
No,
that. Right?
RCOH there is going to be H delta plus there.
C delta plus also there, right?
Highest delta plus is on hydrogen. That is why it is an acid-base reaction. Nah?
Oh, like that. Okay.
Think for a second. Now, why the hell is this guy who is interested in attacking a desperate center going and attacking a carbon? Because the carbon is the only center available here. When there is a hydrogen available with the delta plus, that becomes far more attractive.
Okay, 1 second. Got it. Yeah. So just 1 second. Okay.
Next up,
1 minute, sir.
what other acid derivatives are you familiar with?
Sir, one more thing, like catalytic reduction of functional groups, like there also RCOH is very less reactive with H2 and nickel, right?
Yes.
Is there a similar reason for that? What's the reason for that?
No.
The
reasoning there is going to be slightly different. Hydrogen and nickel is something which is going to be preferring to attack a system which is closer to non-polar. The polarity in the carboxylic acid is very high. Which is
between
also,
O and H or what?
Yeah, we know the O and the H, yeah.
Okay.
So that takes precedence.
What about if we consider the C and double bond?
See, when you're going to be having the C and double bond, what is happening in that C and double bond there? It is having a resonance.
Yeah.
When it has a resonance, what is the actual location where the delta plus is focused in?
Hydrogen.
Correct.
Yeah.
Because of resonance, you'll end up having things. Basically, the hydrogen is going to be the sacrificial lamb at the end of the day, finally. There is no escape for that fellow there.
Yeah.
So think of it as this is a molecule which is heavy in one side, but the lightest side is also going to be extremely weird in its own way. It is also extremely heavy in terms of the charge density it is carrying. So it is, think of it like an axe, a catapult or an axe or whatever it is. something which has got like two different ends. One end is heavier, the other end is lighter. One end is bigger, the other end is smaller. Problem is the smaller end is also heavy in its own way. Except it is not heavy in terms of the mass, but it is heavy in terms of the charge.
Hmm.
You understand the idea there?
Yeah.
So the entire molecule is going to be a wobbly molecule when you're throwing it at any particular system there. And which direction will it basically end up falling on predominantly? Around this region. Basically, this is going to be its most reactive spot. So any reaction which it comes across, it will try to move into that particular, that will be the one which is going to be focused on. If you are not having a hydrogen, then it is not an imbalanced spot there. It is not a tiny location which is having that much charge. It is spread out a little bit more. When it is spread out a little bit more, it is less problematic.
Yeah.
You understand the idea there?
Yes. Yes.
So in that case, this location is going to be more feasibly targetable. Because you want to basically target this location and not get the distraction happening over here.
Yeah.
But if the molecule is something which is like having a hydrogen here, then yeah, nothing can be done. Hydrogen is like a Victoria's Secret model, basically. I mean, maybe not the current ones. I don't know how it works now, but something like that. Whereas the other groups, if they are going to be present, they are like plus size models. They are enough. Now, anyway, coming back, actually, no, now that is a very wrong statement because now Victoria's Secret models are plus size models. Woke thing has basically gone very interesting. But that's not the concern now. Let's come back to this. So the idea here is you end up having, when the hydrogen is present, it will distract from everything else. As when there is no hydrogen, when there are other groups there, the focus is going to be on the carbonyl part of the group there still, which means the reduction happens more easily. Effective.
Okay, sir. Yeah.